Hello guys, welcome to homework number 9. The first problem of the homework focus on concept question 1. It says the wheels on a moving bicycle will have both translational or linear and rotational motions. What is meant by the phrase a rigid body such as a bicycle wheel is in equilibrium? Okay, so in equilibrium it means you have no acceleration. Okay, so it means the body cannot have translational or rotational motion of any kind. No, it can. The body can have translational and rotational motions as long as its translational acceleration and angular acceleration are 0. Correct. The body cannot have, so the correct answer is B, basically. So long as you have no acceleration, you can move at a constant rotational speed. You're also translating like a ball, rolling at a constant angular velocity. So there's no angular acceleration. At the same time, moving with constant linear velocity. So there is no linear acceleration. Okay. Next problem. The drawing illustrates an overhead view of a door and its axis of rotation. The axis is perpendicular to the screen, so the door is moving right and left. So we're looking at the door from the top. There are 4 forces acting on the door, and they have the same magnitude. Rank the torque that each force produces. So torque is the force times distance. So the maximum one is the one that has 90 degrees. So F3 definitely will produce the largest torque. F1 has no torque because it's acting at the point of action, the same as F4, because F4 is acting at this point, but the angle between F4 and here is 0, sine of 0 is 0 because torque is RF sine theta. So if theta is 0, your torque is 0. Is that okay? And when R is 0, in this case, there's no distance between the point you are looking at the axis from rotational axis. That's also 0. So F4 and F1 are 0. So torque 4, torque 1 are 0. Then torque 3 is the maximum. Torque 2 has an angle. By the time we resolve the angle to make it perpendicular, it reduces the value of the force. So the torque becomes, so it's T3, T2. T3 is the highest, followed by T2. Then T1 and T4 are two-way ties. So it's just, it's a 0 for that. Okay, for both of those. So the correct answer is the third one. T3 followed by T2, and T1 and T4 two-way tie. Next problem. So you say the drawing shows the top view of the door, so the same door. So we're looking for the net torque acting on this door. Is that okay? So first of all, let's get this. This torque is going to go about this axis clockwise. Is that okay? And clockwise means negative. Is that okay? So it's going to be 20 times 0.5 for the clockwise one. 20 times 0.5. I call it torque clockwise. I just put the arrow there. So that's 10 Newton meters. So it's negative when you're using clockwise, just the direction. Then for this one, going counterclockwise, so we need to make the force perpendicular to the axis. So it's going to be F2 cos 30. So that's 35 cosine 30 degrees times, then we multiply by the perpendicular distance, 1.1. So this counterclockwise torque. So when I put that in my calculator, 35 cos 30 times 1.1. 33.34. So this is 33.34 Newton meters. So what's the net torque? So it's 33.3 minus 10. So it's going to be 23.3 Newton meters counterclockwise. Okay? So that's the correct answer. Okay, counterclockwise. That's how you get that. Okay, good. Next problem. The drawing shows 2 blocks that are placed at the ends of a massless board. So we don't need to consider the weight of the board. So the board is balanced on a support that serves as an axis of rotation. What is the moment of inertia of the system? So this is just seen as point masses. So mr squared from the rotation mr squared, that gives us there. Is that okay? So the left one is of mass 6.8 kilograms. So we just sum mr squared for each mass, and that gives us the total moment of inertia of the system. So moment of inertia total is moment of inertia due to mass 1 plus moment of inertia due to mass 2 m1 r1 squared plus m2 r2 squared. That solves the problem. So 6.8 is the one on the left times 0.3 squared plus the mass on the right is given as 2 kilograms, so 2 times the distance 0.7 squared. That's it. Is that okay? So 6.8 times 0.3 squared plus 2 times 0.7 squared. 1.6 kilogram meters. Okay, 1.6 kilogram meters squared. So that becomes the moment of inertia of the system. Go to the next problem. It says 3 forces are applied to a solid cylinder as given. So the magnitudes of the forces are F1 cos 15 newtons, F2 and F3. So the radius is given, R1, R2 and R3. Is that okay? The moment of inertia of the cylinder is given. 1/2 mr squared. That's what that's supposed to be. I think it's a typo there. That's 1/2 mr squared. So find the magnitude of angular acceleration of the cylinder about the axis. So we're looking for angular acceleration. So we know that the torque is I alpha. Is that okay? So let's get the net torque. So the net torque is I alpha. So alpha is net torque over I. So the moment of inertia is 1/12 mr2 squared. Is that okay? 1/2 mr2 squared. Is that okay? I think that's what that's saying for that. Okay, so that's the moment of inertia. So let's calculate that. R2 is given to be 0.22, so my moment of inertia is half times the mass of the cylinder 12 times 0.22 squared. Okay, so let's calculate that first. Half of 12 is 6. 6 times 0.22 squared will give us 0.29. So the moment of inertia is 0.29 kilogram meter squared. So the next thing is to find the net torque. So we have several forces acting. So this is the axis of rotation. So this force is acting about the axis of rotation F1, so it has no torque. So this one is acting to R3. So I have F3 R3 and F2 R2. That's my net torque. Is that okay? So my net torque is F2 R2 plus F3 R3. Those are the only ones that cause rotation. F1 is acting straight into the axis of rotation, so it will not cause any rotation. 0.29, just almost cancel that. 0.29 is the moment of inertia we just calculated. Torque net is I alpha. So I said alpha is net torque over I. Net torque is what we are finding. We just got I to be. So net torque I said is F2 R2 plus F3 R3 over 0.29. We just calculated our I to be half mr2 squared. That's how we got 0.29. So what is F2 R2? F2 is 24, R2 is 0.22, 4 times 0.22 plus F3 R3. F3 is 17 times R3 0.1 divided by 0.29. So this is my net torque equals that. Okay. So now for the net torque, F2 is going counterclockwise. F3 is going clockwise. So we need to note that. So the one going counterclockwise will be positive. The one going clockwise will be negative. So this one will be minus right here. So we need to remember that. So now let's solve the problem. So we do 24 times 0.22 minus 17 times 0.1, that's 1.7, 3.58 divided by 0.29, 12.344 or 12.33. So 12.3. So 12.3 is our alpha that we're looking for. radians per second squared, and that solves the problem for us. So next, chapter 9, problem 3. You are installing a new spark plug in your car, and the manual specifies that it be tied into a torque that has a magnitude of 96 Newton meter. So using the data in the figure, determine the magnitude F. So you want an F going about this place. You have this 50 degrees. So if that place is 50 degrees, this is 90, so that angle is 40. So you have your wrench here. You are applying your force here, and the angle here is 40 degrees. That is perpendicular to the wrench. So 0.28 meters is the distance. I need a force perpendicular, so this would be F cosine 40. We bring it here. So it's F cosine 40 times the distance. F cosine 40 times 0.28 equals the torque I'm given, 96. So from there I find F. So F will be 96 divided by 0.28 times cosine 40. 96 over cosine 40 times 0.28. That gives us the answer for that one. So let's do that. Make sure we get the correct answer. 96 divided by cosine 40 is that, divided by 0.28, 447.6 exactly, 447.57 that you have there. So it gives us 447.57 newtons. So that's the force required to bring that torque. So chapter 9, problem 12 says the figure shows a person whose weight is given doing push-ups. Find the normal force exerted by the floor on each hand and on each foot. So let's look at that. So the hands and the foot are the support. So we're going to take them as one support. Find the force on that support and then divide by 2 for each hand and each foot. So that's the trick. So we just have, we're just going to take this guy to be on 2 supports. Okay. So we have the center of gravity here. So the weight of this guy is given to be 788 newtons. And this distance is 0.41 meters. And this distance is 0.84 meters. So I have support 1, say hand support. Support 2, say foot support. So if I take my torque about this guy, so this is going to be counterclockwise and this is going to be clockwise. I take the rest of the force there. So my clockwise one will be 0.84 times 788 equals my counterclockwise one, h times 0.84 plus 0.41. So I need to sum those. That's the total distance there. 0.84 plus 0.41. 1.25. 1.25. So my h becomes 0.84 times 788 divided by 1.25. So 0.84 times 788 divided by 1.25. 529.5. So that's the hands, both hands. So I divide that by 2 for both hands. It gives me 264.8 for both hands, for each hand. So h over 2 for each hand is 264.8 newtons. But this one alone will give us double of that. Now for the feet, there are 2 ways to go about it, the long way and the short way. The long way is to do what you just did, but taking the moment or the torque about h. So this becomes clockwise with the same distance, 1.25. And this is counterclockwise, 0.41. But that's too long. Since I've already gotten h as one upward force, I use the first law of equilibrium, that downward forces equals upward forces. So 788 must balance. So this is 264.8. That's 529. That's what we got before. 529.54. Before we divided for each hand. So 529.54 for both hands here. So let's get for both feet. 529.54 plus feet. So downward forces 1 equals both support upward forces. From there I get feet and then divide by 2 for each foot. Okay, so I do 788 minus 529.54 is 258.46. That's for both foot, so I divide that by 2. 129.2 exactly for each foot. So each foot divided by 2 is 129.2 newtons. That solves the problem for this part. Okay, next question. So it says that a person exerts a horizontal force of 190 newton in the test apparatus shown in the figure. Find the horizontal force M that his flexor muscle exerts on his forearm. Okay, the flexor muscle on his forearm. Okay, so he's applying that that force there. Is that okay? And then he's pulling, and that is pulling back, and his forearm is pulling that way, and then you have the distance from his forearm. Is that okay? To the elbow joint. So this is what we have basically. Okay. I'm going to draw this in a much easier way with straight lines instead of the arm. So I have this. This is the point, the pivot. I have one force this way, I have another force that way. Simple. This is what's going on. Okay? So I have 190 Newton here. I have 0.34 down. And I have 0.054 here. And I'm asked to find F. So this will come here. This will go counterclockwise, and this one will come clockwise. So 190 times 0.34 is my clockwise. I equate it to my counterclockwise. When I'm equating clockwise and counterclockwise, I don't need to put minus. I only put minus when I'm summing clockwise and counterclockwise equals 0. Okay? So force times 0.054. That solves the problem. So what is F? 190 times 0.34 divided by 0.054. Okay. So let's do that. 190 times 0.34 divided by 0.054. 1196.3. 1196.3 exactly. That becomes the answer for that problem. Okay. A CD has a mass of 17 grams and a radius of 6 centimeters. When inserted into a player, the CD starts from rest and accelerates to an angular velocity of that. Assuming the CD is a uniform solid disk, determine the net torque acting on it. So let's look at the net torque. Torque is I alpha. Torque is I alpha, so we can solve the problem. So net torque is moment of inertia times alpha. Moment of inertia for a disk is half mr squared. Alpha is omega final minus omega initial over time. And then we're done. Half times the mass, 17 grams, 0.017 kilograms. The radius squared, 6 centimeters, 0.06 squared. Omega final, is that okay? Starts from rest and gets to 29 radians per second. 29 minus 0 because it starts from rest over 0.48 the time. And it's just going to give me my torque. Okay? So I'm just going to do that. 0.06 squared times half times 0.5 times 0.017. It gives us that. Times 29. It gives us that. Divided by 0.48. Gives us that. 0.0018. 0.002. 0.002 Newton meters is the torque we're looking for. The torque we're looking for. Go to the next problem. See what the next problem says. Chapter 9, problem 34. A ceiling fan is turned on, and the net torque of that applied to the blades. The blades have a total moment of inertia. What is the angular acceleration? Simple. Torque is I times alpha. So angular acceleration alpha is torque over I. The torque is given to be 2.1. I is given to be 0.29. So 2.1 divided by 0.29 is what we are looking for. Simple. Excuse me. So let's do that quickly. 2.1 divided by 0.29. 7.24. 7.2 radians per second squared. That solves that problem. Then focus on concept question 15. A hoop is rolling without slipping on a horizontal surface. So it has two types of kinetic energy, translational kinetic energy and rotational kinetic energy. The entire mass of the hoop is concentrated at its rim. So its moment of inertia I is mr squared, where r is the radius. What is the ratio of the translational kinetic energy to the rotational kinetic energy? So it says the answer is 1. So let's do that and see how the answer is 1 for this case. Because we know the formula for translational kinetic energy, and we also know the formula for rotational kinetic energy. So let's take a quick look at that. So translational kinetic energy is half mv squared. Rotational kinetic energy is half moment of inertia omega squared. Just change all the linear values to rotational values. Linear mass, rotational mass is moment of inertia. Linear velocity, rotational or angular velocity is omega. That's it. So they say we should find the ratio of translational to rotational. So we're looking for half mv squared divided by half I omega squared. Is that okay? Is that okay? Good. So it's a hoop. So when it's a hoop, the moment of inertia is just mr squared. So this is half m, v is omega r, so v squared is omega r squared, over half I is giving us mr squared omega squared. So this is half m omega squared r squared over half m omega squared r squared. So that's how they get 1. Just change your v to omega r. Everything becomes the same from under to under. Put your I to be mr squared, and then they look exactly the same, and the ratio becomes 1. Correct. Okay. The next question, focus on concepts. Question 19 says, a diver in mid-air has an angular velocity of that and a moment of inertia of that. He then pulls his arm and legs into a torque position, and his angular velocity changes. So the net external torque acting on the driver is 0. So we want to see the new moment of inertia in the torque position. So this is conservation of angular momentum. Conservation of angular momentum. That's what we're looking at right here. So I1 omega 1 is I2 omega 2. That's all. Initial, final. So 6 times 1.6 equals 12 times I2. So we're looking for I2. So I2 equals 6 times 1.6 over 12. Okay. So 1.6 divided by 2, 0.8 kilogram meter squared. That's all you have there, exactly. Chapter 9, problem 51 says a flywheel is a solid disc that rotates about an axis that is perpendicular to the disc at its center. Rotating flywheels provide a means for storing energy in the form of rotational kinetic energy and are being considered as a possible alternative to batteries in electric cars. The gasoline burned in a 482-mile trip in a typical mid-sized car produces about that joules of energy. How fast would a 43-cell flywheel with the radius of that half to rotate to store this much energy? So they want omega to store that energy. So 1.18 times 10 to the 9 joules, is that okay? Is being converted to half I omega squared. That's it. Half I omega squared. So the omega is a rotating flywheel, a solid disk. So we know that a solid disk is half. So this is half times half mr squared. Then we'll have omega squared. So mass times radius squared. Is that okay? Mass times radius squared. So the radius of the wheel is given and the mass is given, 43.7. So this is half times half is 1/4 times the mass, 43.7 times 0.381 squared times omega squared. Okay. So we are looking for omega squared, basically. So from here, omega becomes the square root of 1.18 times 10 raised to the power 9 times 4 is times 4. Okay. divided by 43.7 times 0.381 squared. Okay, so let's do that. So I have 1.18 times 4 is that, divided by 43.7 is that, divided by 0.381 squared is that, times 10 to the 9, that's 7.4 times 10 to the 8. So this becomes square root of 7.4 times 10, 7.4 times 10 to the 8. So let me get the square root of that. Square root of 7.44, 2.73 times 10 to the 4. So this is in radians per second. They want it in revolutions per minute. So 2 pi radians is 1 revolution. So I'll divide this. So I'm going to convert this to revolution per minute. So let's go there, see how it goes. So this is 2.73 times 10 to the 4 radians over second times 1 revolution is 2 pi radians times 60 seconds is 1 minute. So seconds cancel seconds, radians cancel radians. My answer is revolutions per minute. So I multiply this by 60 divided by 2 pi. So 27300 times 60 divided by 2 pi, 260661. Get 260481. So did we miss something? So maybe we did some approximation. So let's not approximate. Let's go back. 1.18 times 4 is given by that. Divided by 43.7 divided by 0.381 squared .744 times 10 to the 9. Okay. Times 10 to the 8. So take a square root of that. 2.73. Oh, because I approximated here, there's only 2.7277. So let's use that here, times 60 divided by 2 pi divided by 2 divided by 3.142. Yep, 2604445. So it's close in revolutions per minute. Okay. So I'm having 26045 basically. 26045 450. Okay. They had 48. It's pretty close. It depends on how much you approximate when you do this. Okay. Okay. Let's go to the next problem. So a bowling ball encounters a 0.76 meter vertical rise on the way back to the ball rack. As the drawing illustrates, ignore friction loss and assume that the mass of the ball is distributed uniformly. We have translational speed at the bottom and the final speed at the top. So that's what they're asking us to find, the final speed at the top. Okay. So this is what we're going to do. We're going to conserve all energy, rotational and translational, for both bottom and top. So I'm going to have half mv squared plus half I omega squared plus mgh at the bottom equals half mv squared plus half I omega squared plus mgh at the top. Okay. So it's a ball, so I is to 5th mr squared. So I'm just going to call this V1 omega 1 H1, V2 omega 2 H2. Okay. So H1 is 0 at the bottom. I is 2 over 5 mr squared for a sphere. So we can just calculate that. 2/5 times the mass is given oh, we don't have the mass, so we only have the radius. And right, so we're just going to put that there. So this is half times m times initial speed is given at the bottom, 7.79. Is that okay? Plus half times I is 2 over 5 times m times radius squared. We're not giving radius, so we're just going to say r squared plus 0 equals half times m times, we're looking for v2 squared, that's what we're looking for, the final velocity at the top, plus half times 2/5 times m times r squared times m times g times h is given 0.76. Okay, so m's we cancel all through first of all. So let me get half of 7.79 squared. Okay, (7.79 squared divided by 2, 30.3421. Plus 15 mr squared. So the m's have cancelled everywhere. So plus r squared over 5 equals m cancelled, v2 squared over 2 plus m cancelled, r squared over 5, so that doesn't change. Oh, I forgot the omega squared. So there's omega squared. This is the half I omega 1 squared, and this is half I. So there's omega 1 squared here, and there's omega 2 squared here. Okay. Then m cancelled, so we just have GH 9.8 times 0.76. 9.8 times 0.76. 7.448. So this is plus 7.448. Okay. Now, omega 1 squared is V1. Is that okay? V1 R1. So V is R omega. So omega is V over R. So this is plus R squared over 5 times omega is V1 over R squared. So because it's squared, but the R we cancel here equals this same thing here plus R squared over 5 plus V2 squared over R2 squared. So the R will also cancel here. Okay, so let's simplify this further so I can clean this top side since I have my values now. So what I'm going to have is 30.3421 plus V1 squared over 5. I already know V at the bottom. 7.79 squared over 5 equals V2 squared over 2 plus this is just V2 squared over 5 plus 7.448. Good. Now I can find V2. So V2 squared over 2 plus V2 squared over 5 will give us some value V2 squared. Okay. So I have 7.79 squared divided by 5. So I'm going to do that. divided by 5 is that, plus 30.3421 is that, minus 7.448 is that, 35.031. So 35.031 equals 0.5 V2 squared plus 0.2, 0.7 V2 squared. So V2 is square root of 35.031 over 0.7. That's it. Square root of that. And it gives us 7.1 meters per second. Exactly what we have there. So half mv squared initial at the bottom, this is the v squared plus half I omega 1 squared at the bottom plus mgh at the bottom is 0 equals half mv 2 squared at the top plus half I omega 2 squared at the top plus mgh2. So I have that. So I cancel all the m's and I did this and I did that. And I put omega to be v over r and I solve all this crazy stuff and I get v2 at the top to be that. Okay. Well, the last problem is this one. A playground carousel is free to rotate about its center on frictionless bearings and air resistance is negligible. The carousel itself without riders has a moment of inertia of that. When one person is standing on the carousel at a distance of that, from the center, the carousel has an angular velocity of that. So we're looking for the person's mass, okay? So this is a conservation of momentum, but for two bodies now. So we have a person and a carousel. So when the person is standing at some spot, we can get the I of the person. So I person, omega person 1, plus I carousel, omega carousel 1, equals I person, omega person 2, plus I carousel, omega carousel at point 2. That's what we saw. So for the person is just mass times r squared. The distance is from the center of rotation of the carousel. So the moment of inertia of the carousel is given 125. So for the person, his mass and his distance is 1.5 meters. So it's m times 1.5 squared. That's mr squared for the mass of the person times omega of the person. The same angular velocity of 0.6 plus I carousel is 125 times the same 0.6. So this initial equals final mass of the person times a new radius 1.06 squared times a new velocity 0.8 plus 125 times 0.8 for the carousel. That's all. So we look for m. So here 0.6 m times we'll just multiply together. So let's just do the multiplication. 1.5 squared times 0.6. 1.35 m plus 0.6 times 125, 75, plus 0.8 times 1.08 squared, point 933, 125 times 0.8, 100. So 100 minus 75 is 25. 1.35 minus 0.933. 0.417. 1.35 minus 0.933, 0.417 m is 25. So m is 25 over 0.417. $59.95. Okay, they have 55. So let's check what we did wrong. So we'll have mr squared, 1.5 squared times 0.6 for the first one. 1.35. Then the other one is 125 times 0.6, 75. So that's I omega for the other guy. Then omega 2, 1.06 times 0.8. 0.898. So this one is 0.898 or 0.899. Okay, now let's do this again. 1.35, so that's 1.06 squared times 0.8. So that's where we made a mistake, okay? So 1.35 minus that, 0.45112. 0.45112. So 25 divided by 0.45112. Let's see what that gives us. 55.4. Correct. And that is the final answer for the final problem. So you guys have a good one. See you for homework number 10.